Hello everyone, and welcome to another video for Stat 385. So in this video, we're going to talk about iteration, and the main topics are going to be apply functions, and then we'll talk about for loop, while loop, repeats loop, and the concept of break. So in programming, iteration is the concept in which there's where a task is going to be repeated some set number of times, or some number of times, and this can be done or achieved in a variety of different ways. So like we could repeat a task until some condition is met, or we could repeat a task a specific number of times, or repeat for each element of a collection. And each of these, if you've had programming experience before, each of these, those different conditions invoke like a notion of a for loop or a while loop or something like that you've seen before. So in R, however, vectorization, which we've seen before, and then these types of apply functions are going to be what you're going to want to work for the concept of iteration rather than loops. And there's a variety of reasons for that. One reason is just in some, after you get some comfortability with them, writing code with apply functions is just going to be easier to read, easier to write, it's more concise, and in R, oftentimes it is going to be faster. Now, it won't, of course, seem that these functions are easier to write or read because it's new stuff and you may have familiarity with for loops. But for a number of reasons, for loops are, or just, traditional loops are just not the ways to go, and we'll get into some of that here. Okay, so first of all, we are going to work with apply functions, namely lapply. And lapply takes two arguments, traditionally, a list and a function. And so it's going to take a list as an argument, a list with, a set number of objects. It could be a vector, an atomic vector even, and then it's going to apply a function to the elements of that list, applying it element-wise. So there are cases where loops, like traditional for loops, will be important if the task at hand involves multiple indexes from a vector simultaneously, because these apply functions work element-wise, independent of the other elements in the vector, and that this will become clear. From our textbook, there's this nice little graphic about what's going on. So the lapply function takes this list of elements, never mind what the elements are, 1 through 5, and a function. And then what the output is the function applied to the first element of the list, function applied to the second element of the list, so forth and so on. Okay, so that's what is happening under the hood here. Okay, so let's try it with a extremely simple example. Okay, so log. So first argument is a list, second element is a function, and this is always going to be first argument list, second argument function, always going to be the case. So I'm not necessarily going to specify x equals or function equals. There'll be cases in which we do either of those things, but generally speaking, this is the convention for writing lapply statements. So we can, as long as we know first argument is some list, in this case a vector, and some function, then we're good. So what is going to happen here? So if we go back to our graphic, we have a vector 1 through 3, we have a function log. Log is getting applied to 1, log will get applied to 2, and log will get applied to 3. It's literally just, the names of the squares. Okay, and then it takes a list or vector as an input, and it's going to return a list of output where log is now applied to each one of the elements of the input list or vector in this case. So great. This works. We can blow it up and it still works, but you may okay, so actually let's just go back, zoom in on 1 through 3 and just show what happens if I break it up, typing in log 1, log 2, log 3, and storing that into a list, and we get the exact same thing. So lapply 1.3 log is the same as list log 1, log 2, log 3. Okay, good. So you may think like, that's great, cool to demonstrate how an lapply function works, but the function itself, log, has built-in vectorization. It can take in a double vector as an input and then return a double vector as output, where the double vector is just more readily convenient. It's now just a vector of length 3, whereas before we had a list of length 3. It's a little bit more unwieldy. Of course, there is a way to get around this, but now we have 2 steps: unlist, lapply, log. Not as fun. Okay. So, and we'll get to a shortcut for this return into vector in just a little bit. Okay, so now let's do something else and start showing a little bit more capabilities of these lapply functions. So I'm going to create a list, a named list, in which I generate some numbers, as I have done many times using this runif function. I'm going to generate 20 realizations, 20 draws from a uniform distribution ranging from 0 to 1. Here, the argument, of course, the first argument is the sample size for the number of draws that I want to make, and so I'm not using it this time. We're moving ahead here. Okay, so I have my list. Let's see what it looks like. Okay, so you can see I have my 20 draws. Okay, so I have 3 collections of 20 draws from a uniform distribution. They're all slightly different, and they form the elements of this list. Okay, great. So now what I can do is, lapply x list, and I can do something like pull out the maximum for each one of these samples of 20 observations. Easy. Okay, great. Oh, one of them is actually pretty close to the theoretical maximum, which is 1. Interesting. Okay, so that's great. Or, again, this is nice now because I have 3 collections of 20, not as straightforward as what we saw earlier with this log function, how that would sort of how vectorization would handle that. But you could still complain about the output being a list when we have each one of the values of this list a numeric vector of size 1. I'm saying numeric type double vector of size 1, where you may want to return an actual vector of size 3 in this case. Now, there are functions which don't output vectors of size 1. For instance, range. Range will return a vector with the minimum value in the sample, I shouldn't say sample, minimum value in the numeric vector, maximum value in the numeric vector. So let's look at that. So now, maybe it's not as straightforward as to what kind of vector you would want to create with this. I mean, you could create a vector with 6 observations, but the first, third, and fifth would correspond to lower values, and the second, fourth, and sixth would correspond to upper values, and it's not exactly clean and clear what that would mean and how to actually wield that in further analyses. So here, list output is probably what's preferred. So anyway, lapply, I take a list as an argument, take a function, apply the function element-wise to the list. Here's our schematic. Okay, great. Okay, so Okay, so now let's get into a little bit more fun. Actually, you know what? I do want to do one thing before I step ahead here. So one thing I can do, I'll take my list that I'm working with, my 3 elements, each one being a sample of size 20 from a uniform distribution. And I am going to now specify this function. Now check this out. I can declare a function inside of lapply. So what I'm doing here is, remember, first element is a list, second element is a function, and I know that the argument is function. I'm just going to, in these cases, I'm building in max. Max gets applied, to each one of these elements of the list. Here I'm going to write a function, a custom function, to apply to the elements of that list, where maybe this is something that I can write concisely and isn't something that I want to use in further analyses. So I'm just gonna just write it right inside. So what I can do is say min x, mean x, median x, and max x. So kind of like a summary output here. So let's see what happens. And I get everything. Min, mean, median, max. Okay. Cool. So, right, so function is an argument in lapply, and I just wrote a simple user supplied function there, and it's not something that I really care about. Didn't get saved into the global environment. It's gone after the call. Okay. Now we'll create a function on the outside and call it in. Oops, why would I do that? Multiply and power. This is going to be a function taking 3 arguments, x, c, and p. And what I'm going to do is I'm going to take x to the p power and then multiply it by a constant, c. Okay, pretty straightforward. Let's try it out. Multiply and power. X equals 2, c equals 5, p equals 2. And I get 20. All right. Yeah, 2 raised to 2 is 4 times 5. Okay, yeah, so it works. All right, nice. So the function has sort of built-in vectorization. So let's say I want to evaluate this at a range of multiplicative constants. So I'm taking 2 to the second power, and I want that for constants from 1 to 5. And great, that just works. Now let's say I want to do the same thing for different values of x. Okay, great, now it complains. Does it work when I do? Okay, I contend that this is probably not the right thing that you would want if you were to write it, even though it is the same length. So what can we do? So we can use an lapply function for this. Okay, so what I'm going to do, say this was my thing of primary concern and that I want to change 2 to 1, 3 here. So what I want to do, 1, 3, okay, so multiply and power. Well, this isn't going to work directly because, well, first of all, I'm not specifying anything for C, and more important, or more to the point, I'm not specifying 1 to 5, and the main thought here might be that that should be a scalar anyways. But like this won't work because the arguments aren't supplied with the default. So what this did was it took the elements from 1 to 3 and it slotted them into whatever the first argument was for our multiply and power function, which was x. And then it went to C and realized that there wasn't anything supplied. Okay, so to get this to work, we're gonna need to go to the documentation. All right, so there's this thing called dots dot dot, which is optional arguments to function. So function is, the function to be applied to each element of x. So I can actually supply arguments to this function inside of lapply with this via this ... thing. Normally, you're not supplying arguments to functions, so it's not something you need to worry about. But here, now suddenly, I want to declare some arguments. Okay, so what are we going to expect to happen here? Okay, so let's think through it. Remember that this right here returned 5 output values ranging C with X fixed at 2. So what this is going to do is return 5 output values at each one of these supplied, or each one of these elements. And that's exactly what we get. So here we didn't have a path forward in doing this double vectorization. And you could fix the glitch by making the two things the same length. But that's really just doing x equals 1, c equals 1, x equals 2, c equals 2. And that's not exactly what you want. So if you wanted all combinations of things, this is what you need to do to get it. Okay, great. All right, so lapply, incredibly useful so far. All right, so so now we talked a little bit about this really annoying. So let's go back to the beginning. Clear the palette a little bit here, going back to the start, 1 through 3 log, and then, you know, but Daniel, this doesn't actually, if I just use the vectorization built into log, I would get a vector. Well, there is an apply function that does this. Okay. 1, 3 log. All right, it's the same thing. So what happened here? So I don't know the reasons why lapply is named lapply. I think it's because it's list as an output, list as an output. List as an input, list as an output. And sapply does this simplification. So simplification, what does this mean? So logical character string, that's what's going to be supplied as an argument for simplify. Should the result be simplified to a vector, matrix, or higher dimensional array if possible? So basically what this is going to do is it's going to, if I specify inside lapply, if I specify simplify equals to true, it's going to guess at a type to sort of collapse everything down into. So if I have, you know, vectors of size, numeric vectors of size 1, all of type double, this is pretty easy. It's just going to suppress it into, it's going to simplify it into a vector of size 3. And so sapply does that automatically. It's just simplify equals true. In fact, if I were to do sapply simplify equals false, I just get lapply. Or, you know, I wonder if I do, oh, it's not even an argument. Okay. So if I do sapply simplify equals false, I just get lapply back, and that's no fun. I have lapply to do the job for me. Okay, so sapply 1 through 3 log creates the vector automatically. Right, so let's go back to our example list of the uniforms, and I could do lapply x list max, as I did before, noting that the maximum in the third sample of 20 uniform draws is pretty close to the theoretical maximum, which is fun. But again, I could just sapply this and have it return as a vector of type double. Okay, cool. So let's see what happens. Okay, so nice. Okay, so there are some other apply functions. I don't use vapply too often. One thing to note, I'm just going to comment it out, is there is a function called apply. And so you may think to yourself with the existence of an apply function that lapply is some kind of like specific special case, and that really we should be learning apply because, L is like, an adjective or, something like that. But really apply does very fundamentally different things. So if we go to it, apply works, well, so far it says X and then function, so it's kind of similar, but then there's this margin argument and what's going on here. But basically the difference is that apply is going to work on an array or a matrix, which a matrix is a more simple, or it's an array with some constraints. And the idea with, or actually it's just a lower dimensional array. The idea with a matrix is, well, that seems kind of like a data frame, right? So a data frame has, a data frame is a list with objects of potentially different types forming the columns. But other than that, it has a set number of rows and a set number of columns. And mathematically, that seems like a matrix, right? N rows, P columns, or M rows, N columns, however, whatever the notation is that you've seen before. So it seems like that would be a matrix, but actually matrix is a very specific type of object in R where it's doesn't have this flexibility as a list of objects of different types that a data frame has. So it's a very, very, very different thing. So for the purposes of this course and data analysis and stuff that we'll go through later, actually lapply is probably the main thing that you're going to want to learn, and apply being very special case. Not to say it isn't useful, but lapply is, I guess, more useful. Okay, so we're teaching lapply, and really primarily the two that I would use are lapply and sapply. And if you want to go down the rabbit hole more, there is tapply, which has its time and place, but this is where most of the action is at. Okay, so now on to loops, which are really getting a bad reputation in this course. So continuing with that theme, I imagine most, if not all, people have heard of a loop before. And so there's this quote that I'm taking from your textbook, which is attributed to unknown, which is, "Welcome to R Club. The first rule of R Club is do not use for loops. The second rule of R Club is do not use for loops. And the third and final rule, if you have to use a for loop, do not grow vectors." And we'll get into what this means. So as said at the start of the lecture, there's a lot of reasons as to why you want to use lapply. It's concise, it's easier to read, it embraces the concept of vectorization, it's easier to write after we've gained some familiarity with it because it is something that is new, and it can be faster than loops. It also is, once you get a sense of what's going on, less prone to weird errors that make R inefficient. Not necessarily errors in the sense that it'll break your code, but just weird coding practices that can make R really, really slow. And that's kind of this, if you're going to use a loop, do not grow vectors. The saving grace to loops is the cases where you want to perform some task on multiple elements of some object. Whereas an lapply statement works element-wise. Okay, so now the much maligned for loop. Okay, so the notation is index in vector, code that does something interesting. Probably could have shortened that. Probably should actually raise some kind of, I don't know. Is this necessary? Is this needed? I think we got the point. Okay, anyways. So let's just look at some specific examples. Okay. and we will contrast it with things that you can do in R. Okay, so one thing to note is that when we are working with some sort of storage vector, we're going to iterate some task, we're going to repeat some task, and we are going to save results in something, we want to actually declare our storage vector up front. Okay, so maybe that's a hassle, considering how nice the apply functions are. Maybe it's not, I don't know. Okay, so now we'll do using I as our index, which is pretty standard. Okay. I equals I squared. Okay, so what is it doing? It's going to, so first of all, okay, I already ran this, but you can see it in the global environment. There's 5 numbers, all 0. It's just a declared thing. So now the first run through this loop, I is set equals to 1. So then the first element is going to be the current index squared, so 1 squared. Second element, and then it's going to go to the start, iterate I, and now I is equal to 2. So then the second element of x will be 2 squared, 4, so forth and so on. Okay, so let's run it, and we get that. Great. Okay, so I mean, it works, right? It's easy to see that it's doing the repetitions correctly. If this is the task that you wanted, then it did the right thing. However, look at what R can do with vectorization. All right, that's the same thing. Much easier to write after you get a little bit of experience with R. Okay, so another thing with this is that this loop can set up, this kind of statement sets up some bad or some potential pitfalls if you're tired, or if you've done a bunch of tasks, or if you have a long day, or just a bunch of things open and operating. And so basically the issue is that you have a 5 to declare your storage vector, and a 1 through 5 for your vector for which the index runs over. And so sometimes I've done this a bunch, where you'll change one and you won't change the other, and then results look really sloppy. Or you change this one, which it's not going to actually look like things were bad, but it's growing a vector. And I say don't do that. The reason why I say don't do that is because it's slow. If vectors get really large, then this actually becomes really slow code. And this is one of the gripes that people sometimes complain about R. They say it's slow. It's like, whoa, it's slow because you're using for loops and you're growing vectors in ways that you don't intend to. But if you use vectorized code, it won't be slow. Okay, anyways. So one way to get around this issue is this nice thing called seek along, where, okay, so I declare x to be a 0 vector of size 5, each element 0. What sequence along does is it takes the vector, pulls out its length, and then does 1 : length to get the sequence of integers for all the integers from 1 to length, in this case 5, which is what we were just inputting naturally. So now if I want to change things here, then it does it all automatically. Okay, fun. All right, that's nice. So that's a good trick. One little thing to see how sequence along works. So obviously this is just going to return 1 through 5. But again, the important thing is here is that this is a vector of length 5. So that also returns 1 to 5. So it does exactly what I said. Good. Okay. Nice. So now a case where we will demonstrate a case where a for loop is actually decent. Okay. Okay, so I'm going to create 10 my storage vector will be of size 10. And let's do what we just talked about. Except spell it right, sequence along X. Okay. Oh, and I can, I think it's better practice to actually, I haven't been doing this. Okay. For is not a function. It's a keyword indicating that we're going to do a for loop. Okay. All right, so now what I want to do is do a complicated sequence where I'm starting with 0, and I want to make the first element of my sequence some value. Okay. And now I want to make the second element of my sequence, some value. We'll do, I don't know, 35, sure. And then for the remainder of things, I want to do something like, how about 5 times I minus 1 divided by I minus 2 Great. Okay. So now I have a sequence that, off the top of my head, I don't really know what the formula would be for each iteration of the index. So I couldn't simply write this as an apply function. If I thought about it, maybe I could, but I don't know it. So if my task was to declare 2 values, and then write the sequence current observation equals 3 times previous observation divided by 2 observations in the past, yeah, I could mathematically play with that and see what the recursion is and then figure that out. Or I could just write a for loop. Okay. And, oh, what happened? What did I do? Oh, silly. Okay, forgot to assign it. There we go. Yeah, you can see that it's repeating. What happens if I change it? Yeah, you can see that there's 20, 35, 8.7, 1.2, 5.7, 2.8, 5.7, 20, 35. Yeah, so it's repeating. I just don't know what the pattern is. So I can't, I might can figure it out, but that's gonna take some time. So for loop, great. That's good for that kind of task. Okay. So what happens if, okay, let's do another thing here. Is even equals function x, and we're gonna have this function return this logical statement. So basically, if x divided by 2, or it has a remainder of 0, then this is going to be true. And x divided by 2 has a remainder of not 0, then it's going to be false. So is even. All right, nice. So let's create some data. Just to give it a little bit of space, and we'll say y equals sample 1 through 20. No, 1 through 10. Size equals 20. We'll pull some values. Place equals true. Just out of curiosity, what happens if I do false? It's going to complain. Why did it complain? Because I have 10 objects. I'm making 20 draws, and once I make a draw, I'm not putting it back into the pot, so therefore I run out. Some something to be careful about. All right, great, so now I have some data. And I have a collection of even of odds. Okay, so say I do I am 1 in y. Okay, so this is going to iterate over the elements of y, which is valid. But what happens if I do this? Any guesses? Think about it, pause it, I don't know. Or just watch, because I'm gonna hit the button. Okay, so it runs. Oh, well, first, that's anticlimactic. I actually need to declare, store the function. Okay, so it ran, but I get this. And that's really not what we want at all. What happened? Well, one problem is I have, okay, so first problem is I have a vector of size 20, only taking the values 1 to 10. So this thing can only work on the first 10 elements of the 20 of the vector of size 20. Second problem, this is logical and it's working with a numeric vector. As soon as the logical element gets put into it, its type gets coerced to numeric instantly, and so that's 1 for 1 for true, 0 for false. And since there's multiple values in here, these true falses aren't necessarily going to line up correctly. So like, well, y is gone. What was y? So y, so 1, 2, 3, 4, 5, 2, 3, 4, 5, 6. So here, for instance, we have a element 1, which is now considered even. It's just isn't working. Okay, so if you can see how this do I need to declare it again? Okay, so you can see which index it's working on before it does the assignment. So here, the first element in y is the first element in y is number 3. So now the third element becomes, is that even I? So 1 is not even, and that gets assigned to the third element. Well, if you go down here, you're going to see, again, there's another third element, and so whatever number this is in I, it's just not, wait, no. Print, okay, so for I in y. Okay, so, what? Oh, right. So, it's just a huge mess. So it is taking the elements out of y, and then it's so first element is 3. Let me see. Okay, first element is 7. Okay, so first element is 7. Sorry, it's late for me, but the show must go on. Okay, so first element is in fact 7. So now I'm returning 7, displaying it. So now the 7th element will be, is that even 7? Second element is 4. Now the 4th element is that even 4, so forth and so on. And some of these, you can see will probably get replaced. But at the end of the day, we're going to have this kind of behavior going on. Okay, very, very annoying. Okay. All right, so what we actually want to do is something like this. And I contend that this probably won't work either. I don't need the present statement. We're gonna get a new vector. Okay, so what happens here? So again, I'm taking a numeric vector, y, and I'm reassigning elements of it, and I'm reassigning elements to be something that is logical, and the rest of the elements being numeric. So type coercion is going to happen. This should just be a vector of ones and zeros. And it is for some of the elements. Wait, what's going on? Oh, wait. Sorry, that's right. I want to do this for all of the elements, not just. Okay, there. Now if I do from 1 to 20, I can get the first element of y. Is it even? Assign it to the first element of y again. Simplifying the type. Okay, but because the assignment is something that's logical and the rest of the things are numeric, it's type coercion's happening. Okay. Man, that was a long story for something that was not that hard. Okay, so right, coercion being a big problem here. Now, how about same task, we'll create a new vector y, we'll start over. Okay, new vector y. Now I'm going to pre-allocate a storage vector, logical, length y. Okay. Now, in sequence, along y. Okay. I will assign result to be is underscore even yi. Okay. And did this get something? Finally. Does it work? Well, 10 is even, 3 is odd, 2 is even. Okay, yeah, okay, looks good. Great. But just to keep in mind for this mess of how do we construct the right for loop, well, y is something, or is that even is something that is vectorized. All right, so we could have just done this. All right, so for loops can be a bit of a headache. R is vectorized. Use vectorization. Okay. All right, so one more concept that we'll cover. This video is getting a little bit long. A while loop. And the syntax for a while loop is this. Okay, so while a condition is satisfied, run code. Okay, so let's just go through it. So I have in my, the tasks that I do for data analysis, research, creating my own functions, creating my own R packages, which contain a set of functions. I have more or less completely scrapped for loops out of the equation. Occasionally, I will use a while loop for something. So running a set number of tasks until a condition becomes satisfied is something that can be useful from time to time. But I try to write code. I try to use these apply functions whenever I can. Okay, so let's create some data. Okay. And now let's create a very simple while loop. So while x is greater than 0, we'll just print x. And we will create y to be x equals x over 2. So here x is going to serve as a counter and as an input. And we will allow x to iterate. So I've done some line search type optimization problems in which, you want to do something until something is, you don't know how many steps it's going to take until your answer is found. And so this is the kind of problem where you just keep iterating until some kind of condition happens. Of course, here it's very, very simple because I'm creating x up front, and here it's obviously true, and then I can kind of guess at when this is going to eventually cut off. So what happened? So I created y. Of course, I'm allowing y to grow, which can be strange, but I see that I get the squares again. This is that for loop that we created at the start, written a slightly different way. Fun. Okay, and then x should be 0, right? So I get to 1, and then here it's 1. That's what printed at the end. And then y, x equals 1. So y1 equals 1, and then x iterates down to 0, condition is no longer satisfied, so it breaks. All right, nice. So one more example here. Create x equals 1, y equals 0. This is more interesting. While task is above machine tolerance for evaluating different doubles. This concept, of course, is something very useful. So what did I talk about in the last lecture? Oh yeah, when we added 0.2 to 0.1 and talked about floating point arithmetic, that the difference between those two things in 0.3, how R stores it, is very, 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 very small, but they're not actually equal. And so, machine, oh wait, no, I want this one. This shows kind of the maximum precision we have for differentiating numbers, or the minimum allowable difference between numbers that we can actually work with reliably. And this becomes very, very much of a headache if we want to do something like calculate the null space of a matrix in mathematics, or determining when an eigenvalue is 0 or if it's very small. Sometimes that may require just tell the user you need to actually supply what the tolerance is for making that determination. Anyways, okay, so let's do this. We are going to iterate y, and we are going to shrink x by a factor of 2. So x starts out at 1, y starts out at 0. And so basically what this is going to perform is 1/2 plus 1/4 plus 1/8, or the sum of 1/2 raised to the power k for some set number of until this condition is satisfied. And so it should be very, very small. This means something that converges. This geometric series converges, so it should be close to 2. All right. So it worked. It did something. It is 2. Well, it's not 2, right? Identical. Yeah. That's right. Good. We can bring back stuff that we just talked about. All dot equal. Aha. It's almost 2. Great. All right. So There's also a concept called repeat loop. I'm not going to demonstrate them because we've taken a lot of time and I never use it. And so that should say about how often, how important it is. Well, I shouldn't say that because I use something means it's important, but I don't see too many cases where this is useful and I haven't come across it and I don't know people who use it. Okay, so I will say that. Okay, so thank you for your attention. I should say we should sort of just wrap this up. Okay, so in R, vectorization is extremely important. And then I guess expanding on vectorization is this notion of apply functions, which can take a vector, apply a function to perform some task element-wise, returning a list of outputs where each element of the list is the function evaluated at each one of the elements separately. And of course, if these have some kind of obvious type, then we could use sapply or something. Okay. This is something that may be hard to see now because it is new, but we can see that in some cases where it has some clear advantages over for loops, over apply functions can enhance vectorization, which we saw in this example right here, where we wanted to do some sort of double vectorization, but couldn't quite do it in a streamlined manner. However, in one line, we can achieve the task that we wanted. And we can see a lot of potential pitfalls with for loops in R. One being that we can reproduce a lot of these tasks using either vectorization or apply functions. But there is, if a task does require working on multiple elements of a vector simultaneously, then perhaps a for loop may be the way to go. That doesn't happen too much in the things that I do, but it is possible. And then there are while loops, which we covered some very base cases here, but these do come up from time to time. But foremost, what you want to be doing in R is working with vectorization and apply functions. Okay, so thank you for your attention. Take care, and I will see you next time. If you made it to the end, good job. Thank you. All right, bye.